All right, so here's an example of how to calculate formal charge. And I thought I would do this with sulfur trioxide, SO3. So let's do the Lewis structure first. I've got sulfur coming in with 6 valence electrons. Oxygen coming in with 6 as well, and there's 3 of them for a total of 24. Hopefully now you're seeing this pattern that if you've got 24 electrons and 4 atoms, it's trigonal, planar, and it's always going to be flat. Take that shape. The bond angle is 120 degrees. So this, we could draw the resonance structures because the double bond could be here, or it could be here, or it could be here. We're not going to do that at this point because right now we're focusing on formal charge. So I'm going to do the formal charge first of all for the sulfur. So sulfur's formal charge is going to be the number of incoming valence electrons, which in this case is going to be 6. That comes from the periodic table, minus number of unbonded electrons. Well, there's no unbonded electrons because they're all bonded. They're all wrapped up in these single and double bonds. So that's going to be 0, plus half of the number of bonded electrons. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to have 1/2 of 8, or half, or however many lines I've got. So this is going to turn into 6 minus 4, which is going to be a +2 charge. So sulfur is going to have a +2 formal charge. Let's look at the double bonded oxygen now. Oxygen with the double bonds. Oxygen is going to come in with 6. It's going to have 1, 2, 3, 4 unbonded electrons. And it's going to have 4 bonded electrons. So half of 4 is 2 lines. So then I'm going to have 6 minus 4 plus 2 is going to be 6. And so that double bonded oxygen is going to have a formal charge of 0. Let's look at the single bonded oxygens. Single bonded oxygens, I'm going to have 6 minus, I've got 1, 2, 3, 4, 5, 6 unbonded electrons plus 1/2 of 2 electrons, or 1 line. So that's going to turn into 6 minus 7, which is going to be a -1. Both of these are going to have a -1 charge. We know it's a valid Lewis structure if all of the formal charges are as close to 0 as possible, or 0. And I know this one is 0 because I've got a +2, -1, -1, so the overall formal charge is 0. This is a good check on how we know our Lewis structures are valid. Another example. Carbon dioxide, CO2. We can have 2 possibilities. We have the one that we've drawn previously. And yes, I am skipping doing the valence electrons right now, counting them up. But we haven't ever explored this option. In this structure, you need 16 electrons. I've got 2, 4, 6, 8, 10, 12, 14, 16 here. 2, 4, 6, 8, 10, 12, 14, 16 here. They're both same sound and seem valid. Let's check the formal charges to see which one is more valid. So on this one, carbon is coming in with 4 valence electrons, minus 0 unbonded, plus half of 8. So 4 minus 4 is going to be 0. So that carbon has a 0 charge. Let's go over to this side. Carbon here is going to come in with 4 minus It has no unbonded electrons, and it has 1/2 of 8 again, which will give us a charge of 0. So right now they're tied. Both the carbons are equal to each other. Let's look at the oxygen over here. Oxygen over here is coming in with 6 minus, you've got 4 unbonded electrons plus 1/2 of 8, which is going to be 1/2 of 4, excuse me. 1/2 of 4, which is going to give me a total of 6 minus 6. So that carbon is 0, or that oxygen is 0. That oxygen is going to be 0. Very valid fluid structure because my overall formal charges add up to 0. However, over here, you're going to see something different. The single bonded oxygen is going to come in with 6 minus 6 plus 1/2 of 2. That's going to give you a -1.
Students and staff, please excuse this interruption.
Okay, see if we can get this done before crew type starts. So the oxygen that's double bonded is going to come in with 6 minus, and then I've got 2 unbonded electrons plus 1/2 of 6. So that's going to give me a total of 6 minus 5, which is a +1. So, yeah, it is a valid fluid structure, absolutely, but it's not as valid as the first one because the charges have to force each other to balance each other out. Whereas in our typical carbon dioxide, all the charges already balance out. So, yep, valid resonance structure. You might find 0.1% of carbon dioxide looking like this in nature, but the majority will be this one because you don't have to balance out your charges. Hopefully that made a little bit of sense. Good luck.